Hello everyone, this is Dr. Lennon, and we're going to talk about how we can use calculus in polar coordinates in this video. So let's jump right in. One of the things we care about, two of the main things we care about in calculus are finding slopes of tangent lines. That's the primary focus of Calc 1, and then with integral calculus you focus on areas under curves. So let's kind of cover both of those topics in some detail. So let's start with slopes of tangent lines. So the problem here is typically our functions we're going to write as r is some function of theta, right? That's how we write our curves. And it might be tempting to think, oh, okay, so if we want to find the derivative, so the goal is to find dy dx using these coordinate variables. And you might think, oh, well, maybe it's easy. Maybe it's just dr d theta. Maybe it works just like the Cartesian system. But that's not the case. It's not that simple because we have some product rules kind of involved. So unfortunately, dy dx is not just going to be found by using dr d theta. That's not the case. So let's go back to how the coordinates themselves were related, and maybe we can figure out the derivative from there. So basically we have x is r times the cosine of theta, and so let's say recall, and we also have that y is r times the sine of theta. Well, what's going on is we can replace that r with f of theta now, because that's what r is really representing. And same thing for y. Y is going to be f of theta times the sine of theta. So what does that mean? That means what we have going on here is we have a product rule that we have to figure out, right? So we want to take the derivative with both of these things with respect to theta, and we see that dx d theta is going to be f prime of theta times the cosine of theta minus f of theta times the sine of theta. And if you do dy d theta, we have f prime of theta times the sine of theta plus f of theta times the cosine of theta. So we can combine these to actually get the correct derivative for dy dx. So dy dx here is actually going to be dy d theta over dx d theta. And that's essentially just the two things we wrote down being divided by each other. So we get f prime of theta sine of theta plus f of theta cosine of theta divided by f prime of theta cosine of theta minus f of theta sine of theta. So that is the formula for the tangent line there. So this is how we can use calculus to find the slope of tangent lines given polar equations. Again, so right, there's always pros and cons to working with some things. In some case, some of the graphs have simpler equations when we use polar coordinates, but again, now we see that the tangent line computation can be a bit more complicated here. So let's go ahead and look at an example. So let's find the slopes of the lines tangent to the circle. R equals f of theta, which in this case is just going to be 10. Okay, so we're just going to use the above formula. So note that if we're looking for dy dx, in this case, f prime of theta is going to be 0, so all the f prime of theta terms are just going to vanish. So we're just going to get the f of theta cosine theta, so that's going to be 10 times the cosine of theta over negative 10 times the sine of theta. And that's it. So our equation here, the 10's both cancel. 10 over 10 is 1, so we can just write this as negative cotangent of theta. And that represents the family of all of our tangent lines to the circle. So whenever you plug in a particular theta value, it's going to give you the tangent slope at that moment. So notice if you plug in, say, for instance, theta equals, let's say, pi over 2, you're going to be right at the top of the circle, so that would have a horizontal tangent line, so that's going to be 0, as you would expect. And if you would plug in, say, 0, you're going to end up with a 0 in the denominator there. Sine of 0 is undefined, so you get undefined, which makes sense because that's going to be a vertical tangent line to the circle. So those values are coming out exactly as we expect. Let's say we did something like pi over 4. Well, I mean, so maybe it would help if I drew the circle. So you can check plugging in all of these values, right? We saw at 0, so theta equals 0, slope undefined. Theta equals pi over 2. Our slope is equal to 0. And then, you know, at 3 pi over 2, or at pi you would get undefined as well, and at 3 pi over 2 you would get 0. What about, say, down here? Let's say we did the 45-degree angle right here. So this would be 7 pi over 4. So if theta is 7 pi over 4, we would expect our slope to be 1, and that's exactly what we get. The cotangent of 7 pi over 4 is negative 1, and then the negative on the outside makes it positive 1. So we're getting all the expected tangent lines. Again, the formula is a little complicated, and you might not remember it off the top of your head. The important thing to remember is that dy dx is not going to be the same thing as dr d theta, and when you're working with it, if you have to, just go back to the polar conversion from Cartesian, from polar to Cartesian, and derive it from there. Okay, so let's talk about the other thing that we mainly use calculus for, finding areas below curves, and how we can do that with polar curves as well. So areas of regions bounded by polar curves. So this is what we've got. And basically the idea is you're just kind of rotating. So let's think about the picture. We're rotating through an angle now. We're not rotating either from bottom to top or left to right like we do integrating with respect to an x or a y. Now we're going to be integrating with respect to theta. So let's say we have some curve, and maybe the curve is over here. We have some r equals f of theta. And what happens is we're essentially rotating counterclockwise to figuring out, maybe we're finding the region, the area between two curves. So this one is r equals g of theta. So let's say we want to rotate between here and here. So this one right here is this angle. Let's say, let me draw it out a little farther. This we'll say is theta equals some angle, maybe alpha, and this one up here is theta equals some angle beta. And if we're trying to figure out the region of this area here, what are we going to do? Well, we're obviously going to be integrating between, so the area, let's say the shaded area, we're going to be integrating between those two angles from alpha to beta, and what's going on here is that essentially we're taking slices of circles. So each little sector that we have, when you go to an infinitesimal slice, it looks like the slice of some very small circle. And if you remember, the formula for the area of a circle is pi r squared. So the sector formula for the circle is in general going to be, we're going to have 1/2 times f of theta squared d theta. So we're going to get the same thing here, but since we have two curves in this picture, we're going to be subtracting those curves. So we're going to have 1/2 f of theta squared minus g of theta squared d theta. So that's our area formula when we're looking at the area between two curves. If you're just looking from of say one region between that and the origin that you're integrating from, you can remove the g of theta and just do 1/2 f of theta squared, but this is more general. So, you know, we can do this for a lot of the graphs that we looked at. Maybe it's good practice. You know, we could check, for instance, one of the really basic ones. So let's say example, use the above formula to find the area of the circle. That way we can check our answer to make sure it makes sense, since we know the area formula of a circle from geometry. Let's just say r equals 3, right? Basically our answer should come out to pi r squared, right? So we should get 9 pi as our answer. So let's assume that. Okay, so from our picture, to do one full rotation, we need to go from 0 to 2 pi, so that would be how we would have to integrate this. So the area here would be the integral from 0 to 2 pi, and then we have 1/2, and then we have our f of theta, which in this case is just 3 squared d theta. So we end up with 9/2. Antiderivative of 9/2 is going to be 9/2 theta, and we're integrating from 0 to 2 pi, and so we see that we get exactly 9 pi, which is what we know to be the correct answer from the geometry formula. So this formula is working with that as well. That's not such an interesting example, but let's go ahead and look at one of the rose curves and do that area as well. So example, let's go ahead and find the area of the 4-leaf rose. Let's say r equals f of theta equals 2 times the cosine of 2 theta. So remember that 2 inside the parentheses is an even number, so that's why this this shape is going to have 4 leaves on it, if you recall from the polar coordinates video. So there's a lot of ways to do this. Maybe one of the easiest ways, so if we draw this picture, we could go to Desmos and look up the graph, but I'll just draw you a quick summary. Basically, we have 4 petals. We have this one. We have this one. There's no overlap or anything, and everything's perfectly symmetrical. And we have this one. So it draws this entire rows in 2 pi, right? We go through the entire cosine. Actually, in this case, yeah, so if we draw this one particular region right here, this is drawn from 0. So let's say drawn from theta equals 0 to theta equals pi over 4. And that's 1/2 of one petal, so that's going to be 1/8 of the entire area. So if we want to figure out the area, we can just use symmetry and multiply that by 8. So let's go ahead and do that. So the area here is going to be 8 times the integral from 0 to pi over 4. And it's going to be 1/2 times our formula here, squared cosine 2 times the cosine of 2 theta, quantity squared d theta. So if you multiply that out, scoring the 2, we get a 4 times the 1/2, which is a 2. And if we bring that out front and multiply it by the 8, we now have 16. And we're integrating from 0 to pi over 4. And this is going to be cosine squared 2 theta d theta. And the way that we integrate this, remember, is we apply the half angle formula to cosine. So this is going to be exactly 16 times the integral from 0 to pi over 4 of 1 plus the cosine of 4 theta over 2 d theta. So that is the half angle formula for cosine. And then we take the antiderivative. So we're going to have 1/2 theta times the 16. So that's going to be 8 theta. And then we're going to have, when you do the antiderivative of cosine, it's going to be sine, but you're dividing by another 4. So 16 divided by 8 is going to leave us with 2 sine of 4 theta from 0 to pi over 4. And that's going to leave us with, let's see, 8 times pi over 4 is going to be 2 pi. The sine of 4 theta times the pi over 4 is just going to be pi, which goes to 0. And then plugging in 0 also leaves 0. So we actually just get 2 pi. So the area, in fact, of the entire 4 leaf rows is exactly 2 pi. So that's our final answer. Okay, so one last thing we want to talk about, since we talked about arc length before, let's go ahead and talk about the arc length of a polar curve, because that's also going to be something that we're interested in. So the arc length of a polar curve. So again, let's say, suppose that we have a differentiable function, so let f have a continuous first derivative. On interval AB, or let's say alpha beta, those are better names for angles, on alpha beta. The arc length is given by, so we're going to integrate from alpha to beta, and we're going to be taking the integral of f of theta squared plus f prime of theta squared. And I'm not going to go over the proof of that. We're just going to use it. Again, if you want to know the proof, it essentially comes from taking the arc length formula we know and then replacing the typical dx squared plus dy squared with the dx d theta that we were using previously. So the way that we derived the formula for the slopes of tangent lines, there's going to be a similar type of argument there where we need to care about the derivatives. But it relates to putting that together with the arc length formula that we know for Cartesian coordinates. So let's go ahead and just do one quick example, and then we'll call it a day. So example, let's go back to that spiral of Archimedes. So find the arc length of the spiral r equals f of theta equals theta, right? Just r equals theta was the spiral of Archimedes. For 0 less than or equal to theta less than or equal to 2 pi. So how long is that curve exactly? What we want to do here is we have our length. We're integrating from 0 to 2 pi. And we're doing the square root. We know f of theta in this case is just theta, so it's going to be theta squared. And then the derivative of theta is just 1, so it's going to be the integral of theta squared plus 1 d theta. And for this one, remember, if you have theta squared plus 1, you can either look it up using a table or using the trigonometric substitution. So I'm going to go ahead and just use the table. If you want to recall trigonometric substitution, you can go back and apply that method as well. Again, remember, it's typically just taking advantage of the Pythagorean identity in one form or the other. But anyway, so the antiderivative of this is going to look like theta over 2 times the square root of theta squared plus 1 plus 1/2 the natural log of theta plus the square root of theta squared plus 1, going from 0 to 2 pi. Okay, so when you plug all that in, you get some really complicated answer. I'll just give you the approximation. It's approximately 21.26. Again, so a lot of times these arc length formulas can give rise to things that are really nasty, but again, the formula in principle is pretty similar to the other ones we've done. It's just combined with the conversion using polar coordinates. Okay, so those are the basic tools of calculus involving polar coordinates. So this is Dr. Lennon signing off.